Hello everybody and welcome to WebAssembly Unleashed, your source for news and views about the world of WebAssembly. I'm your host Joel Moses. Alongside me, as always, my fellow WebAssembly aficionados, fans, and superstars, Oscar Spencer and Matt Iacobucci. How you guys doing?
Doing great.
All right,
Great to be
great.
here per usual.
Yeah, excellent.
Now, we've been doing WebAssembly Unleashed now for a little while, and we want to take a moment out of our busy schedule to thank everybody for watching. We know you have a choice of podcasts to wet your technology whistle these days, and we're glad you chose to fly with us. I am really excited about our WASM community guest today. He is somebody we know very well, is a very familiar face around the office. But first, as always, let's introduce my compadres, Oscar Spencer and Matt Iacobucci. Welcome, guys.
Hey, thanks.
Oscar, what's going on in your world? I hear some good things going on in Austin.
Yeah, one of the things that's really been exciting for me is there's a formal methods meetup that's kicked off in Austin, which is super exciting and very relevant to the guest that we're bringing on the show today.
Oh, yeah.
But it's been amazing just to go to these meetings and just really kick off learning, because as a computer science nerd and one who like loves compilers and things, it's really exciting to hear like, hey, we can prove things about our code. We can verify that code does what we say it does. It's truly fascinating. So I'm super excited about that and glad that we're going to maybe explore some more of that today.
All right. Well, with Matt and with Oscar, let's get right into it because that's a really good introduction, Oscar. I want to bring on Chris Fallon. Chris is, of course, the one of the authors of Crane Lift, one of the most prominent compilers in the community, and just an all-around Mozilla alum and JavaScript expert and all sorts of different things. I could go on, but it would just get ridiculous after a while. We have a topic that we really want to dig into today, and that is formal verification. And so, Chris, I know that this is an area of intensive research for you. Why don't we just start by, for the folks who are uninitiated into the concept in the audience, what is formal verification and why is it important?
Yeah, so I'll break that down into a few parts. First of all, software is hard, right? So humans write software, and humans make mistakes, and so we have this Platonic ideal of we have the specification for what we want software to do, but we don't always write software that does exactly that. And so formal verification, very simply stated, is using computer software that understands something like theorems or logical reasoning to show that the code that you've written actually does what the specification says it should do. Right? So if you say that I'm incrementing this number and I add 1, then it'll actually check, okay, you added 1 and the end result is x plus 1. And so WebAssembly in particular is an interesting application domain for this technology because we have a sandbox. So WebAssembly is often touted as a secure technology. It's a way of taking untrusted code and putting it inside of a sandbox so that it can't have any effect on the computer aside from what we allow it to do. But that sandbox is actually code, right? That sandbox is other software that is implementing the limitations or the restrictions on the code that we're running. And so if we have a bug in that sandbox implementation, then that code could escape and could do malicious things. Or maybe not even malicious. Maybe it would, maybe it just has some bug and corrupts some files somewhere unintentionally. And so formal verification is particularly interesting here because we can use it to show that the sandbox actually holds. And so that's sort of the holy grail, the thing that we're working toward in our community.
And so let me ask just right off the bat, how does this relate to languages that have really strong type checkers, for example? Like I know one of the things they say about OCaml is if your code compiles, it definitely does what the code said it does, at least. Maybe it doesn't do what you wanted it to do, but it's certainly correct. How does that sort of play into the picture here?
Yeah. The thing that happens in computer science that's really interesting is there are often a few different ideas that are variations on the same thing when you look deeper. And
Yeah.
so a thing that I've heard said that I really like is that types are just little theorems, right? And so you have statically typed code in a language like OCaml or Rust or even C++. And by virtue of the compiler accepting your code, the compiler is agreeing that there's a proof that that type is satisfied. So it could be something as simple as the result of this operation is a string, right? That's a theorem. It's a very simple one. So this is, sort of a continuum where there are different ways to write correct, good bug-free software. And one of the easiest ways is adopting a statically typed language so that you have this base level of assurances for free. And formal verification goes way beyond that, right? There are special languages where you can have special types that encode invariance. You can have a side description of the specification, but types are sort of the entry level for a lot of people.
Right.
And so, WebAssembly obviously is a typed assembly language, right?
Sure.
How is that not good enough?
Well, so a thing that I think is interesting about WASM is that it's an interface, and so you can see the interface from both sides, right? So from the point of view of the consumer of WebAssembly, that is someone who is running a WASM module, you can see the specification for what the sandbox should enforce as a boon, right? As something that's provided to you. And so you're running this code in the sandbox, and you get this secure system as a thing, as a result of consuming WASM or using WASM. But from the other side, and this is the side that I live on, and my coworkers on the WASM team at F5, when we implement that sandbox, these security properties are actually suddenly something that we have to provide instead. And so you could see it as, a promise that once we fulfill it, that's a really valuable thing. But it also sets a high bar for the implementation. And so that's what we've been, working on.
Right. Now, strong typing notwithstanding, obviously that is a language feature, but not every language necessarily has that. What problems can result not having the ability to formally verify your correctness? What does that cause?
Yeah, well, security problems is the scariest one. So I can tell
Sure.
the story from 2021. So I was tech lead of CraneLift from 2020 through end of 2022, and then I've done some other things since, still stayed involved. But in 2021, I woke up one morning, a beautiful morning here in California, and we were getting weird crashes in production. We were running CraneLift, the compiler that I worked on to run WASM on our servers at the company I was at the time. Weird crashes in production, seg faults. The entire daemon was crashing. Uh, and we looked into it further, and we found that it was actually a result of perfectly valid WebAssembly code that was triggering a bug in our compiler and generating machine code that accessed memory outside of the bounds of where it should have
Oof.
accessed. And so it turned out that we got very lucky, and this was a security researcher sort of probing the boundaries of things. But it could have been someone malicious, and we showed later that it could have accessed, in theory, could have been used to
Right.
access arbitrary data of other customers. And so that's kind of the worst case, and that's why we care so much about this topic, to be honest.
Got it.
Let's talk a little bit about execution here. Is this just like is this augmenting your CI or your test suite, or does it replace it? Like let's go back to for people who are very new to formal verification.
Yeah. So they're kind of different levels, and it's again, it's a broad field. And if you want to go all in on theorem provers and all of that, yes, you could run that in CI, but probably it would take too long. So it's a whole specialist field. But there are little things that you can do that like fit into a normal workflow. So I'll give an example. I wrote the register allocator in CraneLift. The register allocator is sort of a core piece of a compiler that decides which machine registers the values live in, right? It's pretty fundamental, and it's pretty gnarly complicated code. And so I was having problems debugging that, right? It's hard to get right. And so I wrote a little thing that I called the checker that basically does a symbolic verification. So it shows that as values flow through with the register assignments that the allocator has chosen, they actually end up in the right place. It does something called abstract interpretation with symbolic values. And this is actually a thing that runs just as a normal test, right? So we can actually turn the flag on for any compilation, and it will validate once the compilation is done. Yes, that answer is correct. And then we can also fuzz with that, right? So fuzzing is the kind of testing where we do random inputs. So we just throw lots of random inputs at the compiler and see that no matter what, we get a good answer. And so this is an example of where we could use a technique that's kind of borrowed from, the formal verification world of symbolic reasoning. But it's actually fast and efficient enough that we could incorporate it into our regular testing.
So what other kinds of tools can we borrow from the formal verification community?
Yeah, I mean, another thing that I found really powerful is just reasoning about invariants and putting those invariants in your type system. So there are places in the compiler where we have, certain invariants around the order in which instructions have to be scheduled, or the way in which we can or can't mutate certain state of the processor.
Mm.
And so we write our code in Rust, and then a domain-specific language on top of that we developed called ISLE. We've developed basically abstractions where we have wrapper types that say it's not just a value, but it's a value in this context, or it's an instruction that has these side effects. And then we develop safe APIs that accept certain types, so that you can only put the Lego blocks together in a certain way.
That's right.
So I think this is really powerful thinking in a lot of, you can think about this in terms of API design with any API, really. You want to encode the invariants in a way such that you can't put the pieces together in the wrong order or in the wrong way. And the more that you can do that, the fewer bugs you prevent by construction.
I mean, that already sounds incredible.
That
Yeah.
does.
I mean, it's kind of magical, right? Like it's mathematical proofs, but for software, is it not?
Yeah, mathematical proof is a good way to clarify that for beginners to this particular thing. It literally is the mathematical proof of correctness, which makes it formal. Let me ask you one thing. A lot of times, we talk to a lot of our customers, and they're doing verification or they're doing bug finding using fuzzing tools, and a lot of folks have led themselves to believe that probably is enough. That through the adoption of type safety and through the adoption of fuzzers within their pipeline, they'll find all the bugs. Now, what do you say to that? Is that an approach that one can take, or are there dangers in that?
I think it's far better than what most people do with most software development. And so honestly, if you're doing fuzzing, you're already like in the top 10%.
Light years ahead.
Yeah. And so we use fuzzing extensively with CraneLift and then with WASM time, the WASM engine built on top of it. And it's honestly magical. It finds so many bugs. And so if you're not doing fuzzing, stop everything right now. Go write some
Go do
fuzz
it.
targets, go write some fuzz harnesses and start doing it. It will find many of your bugs, all of your bugs. There are techniques that others are more qualified than me to talk about how to get the most out of that. The thing about fuzzing, though, is that it is a random search, right? And so basically the idea is that you throw random inputs, and it can be random in certain ways. You can play with the random generation to bias toward interesting inputs, but it's random inputs, and then you have some check on the other end. So run the software with that input, see if the result is what you wanted. And random search, is very CPU intensive, takes a lot of CPU time.
Right.
And may not find the answer because the search space is huge, right? What is the number of all possible WebAssembly programs,
Yeah.
or the number of all possible uses of your API? It's enormous. And so we have gone beyond that. And so part of what I've been involved with CraneLift is this collaboration with some academics that I started 3 or 4 years ago that resulted in actually a paper last year. But we use something called an SMT solver. And so the idea is that so an SMT solver, for those who aren't familiar, is basically an
And
engine.
that stands for like satisfiability modulo theorems.
Yes, exactly. Satisfiability modulo theorems. It's kind of a fancier version of a SAT solver, which some people might have also heard of, but with different kinds of values. And so the idea is it's a logic engine, basically, right? And so you can tell it there are variables, there are logical or arithmetic relationships between the variables. Please prove that like there's no satisfiable answer to this, or there is some counterexample. And so what we do is we actually write a specification for not exactly WebAssembly, but an intermediate representation based on it for the program. So if you have an add instruction, we say that really does mean that the result of the add is this plus this, with binary addition. And then on the output side, we take the machine code, so the ARM64, the Intel instructions, and we say an add instruction on this CPU means exactly this. So we generate the formulas in this logical language, SMT, on both sides, and we ask the SMT solver, is there any input for which these don't match? And it might give us one, and we call that a counterexample, and that's a bug. Or it might say unsatisfiable, which is a very jargony way of saying no, it's actually true. Like that, what you asked for is true for no variables. So there's no input for which there's a bug, right? Which is a very negative way of saying it's bug free. And so we've done that, and we actually have found several bugs that fuzzing missed in the ARM64 backend in particular. Nothing critical so far. No things we would classify as CVEs or sandbox escapes, but it is quite good at finding, the weird corners that you would not have thought of. And, the nice thing about formal verification with something like an SMT solver is when you get the answer that it's correct, it really is correct. It's correct for all inputs. Whereas fuzzing, at most you can say, well, I've thrown a few CPU months of compute at it, and it hasn't
Yeah.
found anything yet. Maybe it's fine, or maybe my fuzz input generation just completely missed a case, right? Who knows?
Right.
Yeah, that immediately leads me to two questions. The first of which is you mentioned that this isn't necessarily for WASM, but for some intermediate representation. How do you prove that your translation from WASM to that intermediate representation is correct?
Yeah, that's a great question. So the thing about any formal verification, any software engineering really, is that it's an engineering discipline, and so there are trade-offs with effort. And so there are full formal verified compilers. There's one called CompCert, there's another called CakeML. And there are, papers written about these, much said about them. The engineering effort taken to build an end-to-end verified proof from the source language all the way to machine code is something like several engineered decades, right? So one engineer for several decades, or multiple engineers for less, but it's an enormous amount of effort, and it limits what you can build as well. You can't build the things that are, the most complicated optimizing compilers. And so we have, in our efforts so far in CraneLift, kind of taken a scoped approach, right? You can think of a Pareto frontier of like there are the like really deep things that are like just for one piece, and then there are the shallower things for the whole pipeline. But we have verified the parts that we think are most likely to have bugs. And so that's sort of some core phases of the compiler. The translation from WASM to what we call CLIF, the CraneLift intermediate format, this IR, is not yet verified. We think we might want to do it in the future, but it's a fairly straightforward, almost one-to-one mapping, so we're not too worried. Yeah.
That's great.
Yeah, that sounds about right. And I think that largely answers my second question, which is how do we know that we've described the invariance correctly of, say, insert this x86 instruction that, is super strange in these, weird ways and whatnot.
Yeah.
Who watches the watchers?
Yeah.
It's a great question. Right? So you write the specification incorrectly and you satisfy that specification, but no one cares because it's the wrong spec. So the thing that we think about with real software formal verification in the real world is ground truth, right? And so the best case is that you have a spec that someone else has written that a lot of tools have verified against, that it's sort of an agreed upon standard, and you can verify directly against that, or maybe something directly derived from that. So the efforts that we've taken so far with the instruction lowering verification, this SMT solver thing I talked about, have actually been based on a formal spec that ARM released for the ARM64 instruction set. So that's actually been really, really positive. And full credit to the grad student and professor collaborators I have who got that working. But even if you don't do that, right, there are ways that you can basically engineer the thing so that it's not likely to have divergences. So the regex checker that I mentioned, we actually have a very simple representation for instructions that's not the full instruction set. It just abstracts down to what are the register reads and writes, and that's it, right? And so, you can make things simple enough, and you can sort of like focus on the right part of the problem such that it's unlikely that your spec will have weird corner cases. So it's a matter of like engineering taste and engineering trade-offs in the end to minimize risk.
Yeah, and you had mentioned CompCert. And my understanding is that CompCert is an absolutely massive project at this point in time, where it basically ends up boiling down to just be one giant proof. But that seems, to me anyway, almost somewhat difficult to reason about. How does someone jump in and contribute to something like that? And so for something like CraneLift, is there going to be a point at which where it's this project is just a whole ton of proof code and that makes it difficult for contributors to hop in and help?
Well, that is, as we say in academia, that's a research problem, right? So, no longer an academic, but I'm still good friends with them. So I think that that's an open question. I think that there is a whole like human/developer experience angle to this, which is really interesting, right? And so some of these things are like almost automatic and they're just happening in the background. So the register allocation checker I mentioned, that's just happening all the time, right? So you make a PR, you merge the PR, and maybe you'll get an email a day later saying like, oh, you messed something up. Here's the counterexample, here's the bug. But for the stuff that's actually been proven with the SMT solver, right now it's kind of on the side, so to speak. So it's been verified by the folks who are driving this project. The dream is that we'll actually integrate this into CI. And so, you can imagine a workflow in the distant future when you make a pull request on GitHub to say, I want to add this special case lower to this, this pattern to this new AR64 instruction that does exactly the right thing. And maybe you'll get a comment on GitHub from some bot running the thing saying, here's the counterexample when you have OX80 whatever, like it's wrong. We're not there yet, but that would be the dream.
That'd be so cool.
Yeah.
Yeah. Now, WebAssembly obviously is going to lots of different places, lots of different form factors. It's being included in a lot of things that we didn't think were possible. I think Google's got a program for creating firmware in WebAssembly, like direct run
Cool.
firmware. And of course, we're working on things like embedded microkernel architectures. What does formal verification give you in terms of verification as it relates to multiple form factors that this technology adopts?
Yeah, well, it's super important, especially in the embedded space, right? The trade-offs are different, but you often have uh, more interesting design points where you can't use some of the system, boundaries or security technologies. So in a desktop, if you or server form factor, if you want the best isolation, maybe you'll do what browsers do, and you'll just, you'll fork a new subprocess and you'll run your WebAssembly within that process. But if you're in an embedded microcontroller with, 16K of RAM or whatever, and you want to run potentially untrusted code, you don't have process boundaries. You don't have, kernel mode and user mode. You don't have all of these nice things. So in some sense, it becomes even more important. I don't think the fundamentals change at all. You still trust or you still need to trust your compiler, maybe even more. You probably want to, apply validation to your runtime executive or your kernel as well. And there are, verified things like SEL4 and others that have been verified for that. But yeah, I think if anything, it's more important the more you get toward the embedded domain.
Yeah, it's really scary to think about because I think about, programs running on a computer all the time where it's like, yeah, bugs happen, security exploits happen, but, it's isolated. But then I start thinking about something like a robotic arm running code
Yeah,
and
yeah.
thinking about, actually, it would be kind of scary if someone managed to get in that system, access data they weren't supposed to, make it do things it wasn't supposed to. That actually sounds terrifying.
Oh, geez,
Yeah.
or like a medical device, right?
True,
Yeah.
yeah.
There are really tight constraints in a lot of embedded. I mean, people talk about, hard real time, so that's like response time, but also
Right.
just availability. It's a completely different domain and way of thinking. I think WebAssembly is well positioned because it has the formal specification. It says these are exactly the boundaries.
Right.
But as I said at the beginning, the promise as a user is the obligation as the implementer. And so we really do have to work very hard to make sure those boundaries are real.
Yeah. So if someone wants to learn more about formal verification and they want to get a start with helping with WebAssembly's, how it applies to WebAssembly, how can they get a start?
Yeah, I think just talk to people is the best answer. I actually don't have too much formal, so to speak, training in this either. I just, I have a background in compilers, but I just sort of like read about SMT solvers and whatever. So you can certainly do reading. I think getting into statically typed languages we talked about earlier is a good start for this mode of thinking. Getting into compilers in general or runtimes in general is a good way of thinking about what problems exist, what types of things we might want to prove. And then just talk to people, right? We're friendly in the Wasmtime and Cranelift projects and Bytecode Alliance, the umbrella organization, and we welcome collaboration. So yeah, I just get involved with whatever project excites you, basically.
Yeah, aligned with that. So we've been talking about Cranelift quite a bit. Are there efforts to move formal verification outside of Cranelift, or is that even an appropriate question? Or are there future directions to expand this?
Yeah, like I think the dream within, with my Wasmtime, also Wasmtime core maintainer hat on, I think the dream is that we would have a fully verified WebAssembly VM, right? That's again a
Great.
far future dream. Yeah, I'm not speaking for the project here. This isn't anything concrete, but um, I think that the promise, though, of again WebAssembly is that it is this formal spec, and so you can imagine having tool chains as well, right? That verify, okay, I have this source language that is, has certain properties with types, has certain properties with memory safety, has certain properties with whatever other safety properties, and you could actually verify that the lowering to WebAssembly preserves those properties. And there's been work on that actually, not that I've been involved with, but some other folks I've talked with and collaborated with have done things like memory safe WASM is one example, and others where it's just a really valuable thing in general to have this formal spec that everyone can sort of come together and meet at and use as the point where these proofs get tied together.
Sure, sure. Okay, so if I understand correctly, and I'm going to reiterate because I'm not sure I did, this is all like pretty heady stuff. Like the goal would be we have all these languages with all these different compilers. Those could be formally verified that they're producing the WebAssembly that we care about. Now we've got this formal verification at this other layer that says, look, this WebAssembly does get turned into or transpiled into this proper intermediate representation or the actual machine code that we need. Is
Yeah.
that is that where we're trying to go? That's fascinating. That's excellent.
Yeah, exactly. And there are a lot of invariants there, even just with multiple languages. So another example is there's this thing called the component model, which you can read about elsewhere. That's a big effort in the WebAssembly world.
Yeah.
That is this polyglot linking technology, right? So you have different languages that have interfaces to this commonly specified way of writing APIs. And so there's been work on formally verifying the semantics of that so that you have one language calling another language, and you can actually show that the way that they both handle, types like lists or strings or whatever is using the same representation and is compatible. Because that's sort of my experience in general with bugs in any complicated system like this is that they happen at the boundaries.
Mhm.
Right. So it's more reasonable to look at the core logic and say, okay, I have the correct lowering or the correct implementation of this. But when you have mismatched expectations from two different sides of an interface, that's where the bugs that are really subtle and really dangerous happen.
Right.
So especially having the formal specs for the WASM the core WASM API or the core WASM bytecode, and also the APIs and things like component model is sort of this nice technology that lets us have this meeting point where everything's verified against that.
Now, is this something that is going to require buy-in from the language maintainers, or is this something that the Bytecode Alliance could aid in?
Yeah, I mean, I think that's more of a social question, and that's an open question. I think that there's a lot of grassroots interest for this sort of thing. I don't know that it's at the point where it's like, we have a team ready to go. Give us your compiler, we'll
Mhm.
verify it. This is more just a long-term future goal. And there's building expertise in this, and there are the foundations being built, as I mentioned, verifying or providing formal semantics for the component model. But this is kind of a 5 to 10 year vision, I guess.
Okay, gotcha. Yeah.
Yeah, and we've seen recently on an episode of WebAssembly Unleashed that there are efforts to formally verify the specification of WebAssembly itself. So there's a lot of exciting advancements in this point. And then I'm going to make our show's producer Tabitha very proud when I reference an episode number of WebAssembly Unleashed. In episode 16 of WebAssembly Unleashed with Bruce Gaten, I posed the question: in our new world of AI overlords, we've seen so much code being generated by AI that eventually the code generated by AI will be trained on code that has been generated by AI, and that sounds very scary. Chris, there's totally an opportunity here. What if the AIs all generate proofs from these theorem proving languages, and then the code that we actually get out of them is through program extraction? Is that an actual world we can live in where this is a reasonable way to get code out of all of these AIs?
Yeah, I think that's a really interesting point. So everyone has their own feelings about AI generating code. I certainly have mine. I'm a little old school in that regard, but the thing about AI is that it is, statistical. It is based on a probabilistic model that's saying, okay, the most likely answer to your question is this. The most likely code is this, and everyone is familiar with the problem of hallucinations, right? Or the problem of introducing subtle errors in the code that's generated. And I think if we don't have a check on that, that could actually be disastrous for the world of software. As you allude to, Oscar, we just sort of like degrade over time the quality of our entire code base in the world. And so I think that the more that we can have these guardrails, so to speak, of strongly typed APIs and of some sort of verification on the back end, and basically have a touch point where the humans can say, this is really what we mean in a formal sense. This is really what we want, and don't violate these properties.
Yeah.
Then, in the worst case, we just say, okay, the code that was generated has this error, so we can't use it. But maybe that then feeds back into, okay, how do we fix that error, right? And there's been work on that too, proof repair and all that sort of thing. So yeah, I think that is, in a world where we use AI for, productivity, if we do eventually, then I think that's maybe one of the most promising ways of keeping up the bar of software quality.
Yeah, you've heard it here first, folks. Chris Fallon, fan of
Wow.
AI.
Wow. Wow. I didn't get that, but okay, we'll go with that. So before we wrap up, I kind of want to do something a little bit fun. So in the world of non-formally verified code, obviously bugs exist. And Chris, you told us a story about a CVE a little bit earlier. How about some war stories about what lack of formal verification has wrought? You got any more fun CVE stories for us?
Yeah, well, so there are two CVEs I'm responsible for. I hope that number never goes up, right? I'm human, so I'm sure I'll make mistakes in the future. But the war stories are really just the work on the back end. As anyone who's been involved with running software in production and with security, infrastructure, and all of this is familiar with, it doesn't end with, okay, we found a bug, let's have a PR to fix it. There is a whole process of getting the notifications out to customers and patching, emergency patching. So to the sorts of people who enjoy like incident management, that can be fun. I'm not one of those people. Yeah, formal verification is really important. The sorts of bugs that it prevents have real world consequences, and I think it's important, and we should do more of it.
Absolutely. Well, we're about time to wrap up here. I think that's all the time we have for today. Chris, I want to thank you for giving us a tutorial on formal verification. A really good discussion. As always, thank you, Oscar and Matt.
Yes,
It's a big application world out there. It's time to unleash the power and promise of WebAssembly and formal verification. So, for Chris, for Matt, for Oscar, and myself, thanks for listening in. Be sure to hit like and subscribe for future WebAssembly news and views. Take care.